hello everyone. So I'm Jesper. Today's talk is from Pandas to Polars, achieving 50 times speedups and scaling beyond memory limits. So let's see if we can hold these promises true. So today we're going to talk about why we in CodeLounge moved from Pandas to Polars. We're going to compare, obviously, Pandas with Polars. And then we're going to see how we can use Polars actually with larger than memory datasets. And then finally, we're going to look also some exciting upcoming features in Polars. So this talk, maybe to say, I will show you a lot, also a lot of code, but my purpose is not that you should. I will teach you the API or something like that. It's more to convey how good Polars is compared to Pandas. Okay, so I'm working in CodeLounge, and we have this project called Reflex, Register Your Firm's Life and Exit. It's a Synergia project. I think we are now in the second or third year. Synergia means we are working with other research partners or research groups. In particular, we are working with USI, a research group in economics at ETH and also in St. Gallen. So this project is about economics and also political science. The data, our job is like the data partner. So we have this data set, which is the Swiss Commercial Registry. It started in 1883. They started to make publications, but of course there were no computers, so they printed these publications. Actually, all the way until 2001, it was a printed cassette. Now they have scanned all these into PDFs. So our job is to take these scanned documents and basically extract all these individual entries for each company from 1883 until 2001, so that they then can do their research on that. In these entries we found business founding, liquidations, acquisitions, splittings, relocations, so on. So you can imagine it's very important for studying the economy of Switzerland. So this a little bit the background. That's where we are using Pandas and Polar and data analysis. So far, we have extracted 4.5 million entries from these PDFs. We store them in a CSV file, 2.2 gigabytes, that we are sharing then with the research partners. Yes. Now, we have the CSV file, but then now when we want to work with them on the computer, we have to read them into another format. So as you all know, for data science, a typical format is the data frame or a data structure. It is a two-dimensional data structure. It's like a spreadsheet or a table in a database. It has rows and columns. In particular here, you can, when you have a data frame in Pandas and Polars, you can access the columns as a series and do work on that. Yes. So this is a little bit the background. The Pandas itself, the library started already in 2008, and it was open source in 2009. So it has been around for a while. The original goal by the author was to create a high performance and flexible tool for quantitative analysis on financial data. That was his domain. And since then, of course, it has spread way beyond financial data. It's built on NumPy. Probably many are familiar with that. It has many built-in operations for like arithmetic, string manipulation, summary statistics, and so on. So for data scientists, this is really nice, and therefore also is very, very popular. But over the years, it has also received some criticism, because it's not being efficient enough. In particular, it has quite a high memory consumption. They don't have these kind of query plans, and there's no parallel computing, meaning when you do executions, it will run on a single core on your machine. Pandas 2.0 was released in April last year, so relatively recently. And then there they made a big change, which allowed you to use the Apache Arrow memory model, replacing NumPy. It's still optional, but you can use it and you will see significant benefits of using that. We have now Polars then. So this is new. It's started in 2020 as an open source project. But the version 1 was just released in July this year. So it's really fresh. So it has been very unstable. The original goal here basically was to create an easy to use and performant data frame library, meaning we want to do a better Pandas, basically. And yeah, they want to go beyond these limitations regarding to speed. It also has many built-in operations, and they also have, I don't know, according to us, I think many in CodeLounge think that API is much more intuitive also, which we will see then. They by default have this Apache Arrow memory model, so you get that speed up. It's also written in Rust, so it can do, it's kind of, quite low level language, and the goal here is really to maximize the speed as much as possible. Also, it's parallel by default. So only that, I mean, you now on your machine, you don't have one core, but you have many cores. So already just being that, you will get a big speed up. And now they also have this streaming API where they support larger than memory data sets. So you can do tasks that maybe before were not possible. You needed some kind of distributed library in order to do that. Yeah. And now, very recently, have actually added optional GPU support for speeding up even more. It runs on NVIDIA GPUs, and we will shortly see that towards the end. Okay, so that was a short introduction, and now let's go in and see some code. Yeah. This one. Okay, I hope we all can read. Yeah. So the first point, I mean, it's very simple. It's just loading the data. And already there you will see some benefits. So I'm going to take the data set that I talked about, our Reflex project. Yeah, we can see it's around 2.2 gigabytes. It fits easily in the memory of this machine, no problem. And now we're going to read it with Pandas. Just reading the CSV, the default way of reading this data set. And as you can see, we have to wait a little bit and so on, but okay, 2.2 gigabyte. Okay, maybe we need to wait a little bit. And now it should be finished more or less, I guess. Yes, so in this time, it varies a little bit, now we're running Teams on the machine, so it will be a bit slower. Huh? So here we're talking about 25 seconds, but I mentioned we can also use the PyArrow memory model. So let's do the same thing. We're going to read the CSV file using now PyArrow. Let's see how long that takes. And we see already just changing that, we have now saved, we're more than twice as fast. And now we take the same query, and now we're going to use Polars instead. And now in 1 second. So it's the same CSV. I haven't changed anything, and just like that. Yeah. So basically, the only change we did was the library. We're using PL instead of PD. So yeah. Then we're going to talk a little bit about data types. I think that's also very important, which has a little bit annoying sometimes with Pandas, because you have here, we have read the CSV, but I know that these objects here, they're actually strings. And by default, you will only get an object back. Compare that with Polars, of course, then here we have the proper string data type. Of course, in Polars, I mean in Pandas, we can convert it and say we want a string, but we have to do this explicitly and tell this column is a string and so on. So also this is some additional work always. But yeah, CSV files, you know, maybe not the best format. So we also have the Apache Parquet file format, which is I would say much better file format. It's a column-based, and by being column-based, we can also do efficient compression of the column-wise compression. We can do data skipping when you have a large data set. Maybe you don't want to read all your columns at once. You can select only the columns that you need. Of course, if you're reading by row, you can't do that. Also, another benefit is that the schema is actually stored in the metadata. So basically, these types we saw, you can store them in the metadata. Also, with the compression, we can see, so the same data set now from 2.2 gigabyte is half a gigabyte. So that also is very helpful if you have to store it, send it, or so on. So let's read. We can also read a Parquet file with Pandas. And we can see by default now it's going to switch to the PyArrow engine when you use Parquet. And we are reading, okay, taking a little bit longer here. But around 12 seconds, so it's similar to reading the CSV. Now we do the same with Polars, and again, we are reading around 1 second. It's actually, yeah, it's a little bit faster than reading the CSV. So already here, now we went from over 20 seconds, I don't remember exactly, now to 1 second, reading the same file, just getting the data. Yeah, so let's have a look now a little bit at how to use the API of Polars. So let's read the data. Let's have a look at the data. So we have a data frame, which shows nicely here in the Jupyter notebook. We can see we have an ID, we have the message here that we talked about, the language, the canton, and so on. So this is the data that we have extracted. Now we want to do some queries using a Polars DSL. To do those, you would do so-called expressions. And with this, you express your data transformations. They are lazy representation, meaning you can write them, you can store them in a variable, but they are not being executed at that point. You know? Only when you put them in the Polars context, they will actually materialize. They are very declarative, so it's easy to express your transformations. And also the Polars query engine can do some optimizations when you have, especially when you have many of these. Yeah. So here we have a simple expression. This is nothing to do with this data set, but we just take a weight column divided by the height column multiplied by 2, and here we have it. So we can store, here I have another example. This is more related. So I'm going to do a stupid thing, which is basically taking the company name, or we assume this is the company name. The first part of the message before the comma, we assume this is the company name. This is an expression. I store it in a variable. And now I'm going to tell Polars to select this. So what's going to do is basically do this computation. And now in 1.8 seconds, we were able to extract this string from the 4.4 billion entries we have. Yeah, but this is not stored in the data frame itself. It's just doing this, let's say, on the fly. Of course, we can also store it in the data frame by adding a column. We do that with columns. Here I also do a select to reduce the number of columns we see. Now it's stored in the data frame. Like that. We can do filtering. So in this case, I put 2 filters. we want that the year is 1990. We want to check the entries from Ticino. So we do this filter, and we can see we have 6,500 entries. So all these, we can see already, I mean, although we have quite a large data set, it's very easy to use because you don't have, you click and you wait half a second or a second or something, and you get your result. So this is important also when you're trying out. You know, often the query doesn't work your first time, so this really helps when you're developing. We can also, of course, do grouping and aggregations. In this case here, I want to take the number of compute the number of entries and company names per decade. Decade does not exist, but we have the PDF year. So I do an expression that expresses what is a decade. I group by this decade, and we do aggregation twice, once on the entries and one time on the company names. We're going to extract the unique company names, and then we will do some kind of average entries per company computation, and then we just sort this. So this is a bit more complex, but also here is executing and doing it very quickly. You can also do so-called non-optimized queries. So you can basically call a Python function on each of your elements. This is called the map elements, and we can run this. So, oops. We run this, and we can see that this is going to be slower, depending on what you need to do and so on. But especially when you have larger queries, it's really, I mean, I have some example. I was running some query, and in this way, because it was very complex, I didn't know yet how to write it in Polars. And I was running, maybe it took me 15 minutes. I rewrote it. It took me quite a while. I rewrote it in Polars, and it was executing in 20, 30 seconds. So it was, yeah, really a big difference. Okay, yeah, so I've seen this. Now, a maybe more interesting thing is the lazy API. So I'm going to load again the same data set. With the lazy API, basically, you are going to create your query, but you're not going to execute it. Doing that, Polars can do optimizations on your query, decide what should be executed first, and so on. For example, it can do this predicate push down, meaning you apply your filters early. Projection push down, you select only the columns that it actually needs for the computation. So you write your query, and Polars will do that for you. I mean, as best as possible. I'm sure you can, in some cases, do it better, but yeah. And the difference, what you have to do in the API, you call scan underscore, for example, csv instead of read. And then afterwards, you will have this query, and then to actually execute it, you do dot collect. So we scan the Parquet file, we just get the schema. And to do that, since it's a Parquet file, we don't need to execute it. We very quickly can access the schema. Here we define the lazy query without executing it. Also, this is very quick. Is the same query that we saw before. And we can have a look at it. It shows this kind of query plan. So you can see what steps and how they will happen. Then in this case, it didn't do much changes, but sometimes then it will move, depending on the query, it will move the steps. So, yeah. And then we can execute it by using dot collect. So, and here we can see we execute the same thing. In this case, I mean, the data is not that huge, so it didn't really make such a big difference. But compare this now with Pandas. I will just execute this. So in Pandas, we would the same query. We need to read the whole thing in the memory. We need to compute the different columns that were missing. Then finally we can do the group by. Then to compute this average, we have to do another statement. Then we do the sorting, and then finally we have the final result. And this should more or less be done now, I hope. Yeah, so also this, what we had here was around 5 seconds, and now we're around almost 40 seconds. Okay, so we have seen now many things, but now another very powerful thing is this using larger than memory data sets. Okay, so we're going to read here. We have the data set is called the GitHub torrent. Maybe many of you are familiar with that. I'm not sure. I don't think it's updated anymore, but it used to be a big thing, basically downloading all the commits on GitHub. In this case, we're going to look at commits from 2017 and 2018 because those have been converted and cleaned by Marco to Parquet file format. And just while doing this, I found some blog posts from 2019 where they were attending a Microsoft hackathon where they were analyzing just 1 month of the data, and that was 100 gigabytes compressed. And we will see how much, much better we can do now. And basically, during that hackathon, they were able to do one query, basically, I think. Yeah, which for now is we're doing a fraction of a time. So the data set we have is 217 gigabytes. So it's way bigger than the RAM on this machine, 64 gigabytes. But we can also see so here we have like 24 months. They had 1 month in 100 gigabytes. So using Parquet really is a good thing also for that case. Now, if we would call read on that, it will try to read it and you will run out of memory. So we'll not do that. But we can scan it still. We can have a look at the schema. We can quickly see, okay, it has 34 columns. These are all the columns. These are the types, and so on. We can see some also there's a list of string in that type, for example. So that's interesting. We can also quickly just have a look at the first entries. So that's usually what you do to understand the data better. Very quickly. We can also, let's say, count the number of rows. Now we have to do some more computation, right? But also very quickly, now 291 million rows we have. We're going to try to select the column that doesn't exist, but thanks to the schema, we know it can tell you directly it doesn't exist. You don't have to execute something. Basically, it fails directly. And now we're going to do a stupid multiplication here. No, a stupid addition. But just to show you that we can do this very quickly. Of course, now we're just going to do it at the first, the head. Yes, I do that before I do the collect. But still, this is something you couldn't really do with Pandas. Now we have a little bit more, some query that's a little more involving, where we have to access all the data. So in this case, I want to see how many commits were made on each day of the week. So when are people working? So I have, the first thing I have to do, I have to take the date, and I ask Polars to give me the weekday. It will give me a number 1 to 7. Then I just count, doing a group by on that, and I just count the number of commits. Then we can compute the proportion. So I compare on Monday how many commits were made with respect to all of the commits. And then finally here I'm going to do replace this number 1, 2, 3, 4, 5, 6, 7 with actually the name of the week. So let's execute this. Yeah, and we can see So you have to know, sometimes you have to do the collect and then you have to continue working on the data, right? Because otherwise it wouldn't be available. But also this, quite quickly in 4 seconds, we can see that people are working Monday to Friday, but also quite a lot on the weekends. So additionally to this, we have the so-called streaming API. So at the moment, we were just using the lazy API, reading all this this huge data set. Now, for certain tasks, you maybe need to access all the data in your row, in a column in order to do some computation. To do that, you can use the streaming API, and in this case, I want to get the top 10 authors with the most commits, right? So we do a group by. In this case, I'm just using the author email. And then I'm going to do a collect and I say streaming equal true. So in case, it will not fit in memory, it will split up this execution. But this also so it's very easy. You don't have to do much. Maybe here also, it's taking a little bit longer. Yes, but now we have it in 25 seconds. We can see this guy has a lot of commits. You may wonder why. So, yeah. Okay. Maybe we can, just to show you, I don't know. Okay, yeah, this is what I want to do. I will not rerun the whole query, but just so here I'm looking at my course. Now we're going to start to execute and we can see, boom, now it's not maximizing all the time, but really it's using all your course as needed. Okay. Yeah, so let's switch back now. Here I have a few more slides I wanted to share. No. Okay, so another important point are data formats. And Polars, now it's on version 1, but it already supports a lot of data formats. We have seen CSV, Parquet. It also supports, you can read ND JSON files if you want. You can query your DB, get the data. You can download stuff from your S3 bucket and so forth and so on. Excel files and whatnot. Also, maybe it's interesting for some of you can take a data frame and convert it to PyTorch tensors or PyTorch datasets. That can be very interesting for machine learning, of course. Here are some benchmarks. These are from April this year, so before version 1 was released. Let's see. So we have Polars here in blue. There is another library called DuckDB, and we can see they are very similar in the performance. Here there are some 7 example queries taken from some kind of benchmark data set. But we can see the main point here is this with the Pandas, that we can see the difference. So it's not only the queries I did here, but it's really also for many others. These are run. We also have here PySpark. Maybe many of you know Spark. So maybe to say here also, these were run on a single machine, not like in a distributed context. But these benchmarks come from Polars themselves. So maybe it's not the best. But these DuckDB on their website, they also have they run similar benchmarks, and basically the results are more or less the same. Now, so the next thing, just to briefly mention before we are summarizing, is this with the GPU engine. So I don't know exactly when, but NVIDIA has released kind of a framework or a library to run data analysis stuff on their GPUs. It's called NVIDIA Rapids. So Polars have now integrated this into Polars. And basically, what you need to do is you have your lazy query, you call collect to set your end into GPU. Of course, you need to have a GPU. I don't have an NVIDIA GPU here, so I can't run this. But basically with that, you run it on the GPU. So you may wonder, but what's the benefit of that? And this, again, performance, of course. So here are the same, it's like the same benchmarks as we have seen. Here they have computed, so they're like 22 queries in total. They have summed the execution time when you run it on the CPU, when the data set is 20 gigabyte versus GPU, 40 gigabyte, and then finally 80 gigabyte. And we can see really also here, you don't have to do anything. You just need to have a GPU and you get this kind of speedups, which is quite impressive. It's still in beta, but I'm sure they will release the full version soon. Yeah. Okay, then to summarize, today we have talked about why we in CodeLounge have moved from Pandas to Polars. Hope has been clear. We have comparing to Pandas. We compared Pandas with Polars, and another recommendation: if you're still using Pandas, remember to use Parquet files. We have looked at the Polars lazy API for automatic query optimizations. We looked at the streaming API for larger than memory datasets. They write on the websites it's in development, so it's not supported for all kind of operations, but already for the most common ones. So sometimes it may not work, but you can see this on the website. And then finally, we quickly saw how you can run Polars on the GPU. Okay, thank you very much.